In this video lecture I will discuss about the time dilation that comes under the special theory of relativity. The assumptions are same that I have considered here two frame of references, one is S and second one is S prime. S prime is a stationary form and S prime is a moving frame with the relative speed v, right? O and O prime are observers in S and S prime frame respectively. As I said here, that v is the relative velocity between stationary and the moving frame. So a watch basically or clock is kept into the moving frame, and the time interval between two ticks of the clock is taken by the observer O prime, and that time interval is denoted by the t naught. This time interval is noted by the stationary observer, that is O, and he noted it basically as a t. So t and t naught are the time intervals for observer O and O prime. T naught for the O prime and t for the O observer, that is in rest. So we have to find out a relationship between the t and t naught, and always we remember that t naught is the time interval and the clock was in a moving frame. So in our daily life we see that a spacecraft move with some relative speed with respect to the earth, that one can imagine or assume that suppose is 0.7 c or 0.8 c or near about to the speed of light. So in that situation basically the time interval noted by the pilot of the spacecraft and the time interval for the person who is standing on the surface of the earth will be different. So we have to find out basically that relationship with the help of some numerical problem. So let us see in this particular video lecture, which is based on time dilation. In this video lecture I will discuss about the time dilation that basically comes under the chapter of the special theory of relativity. For the time dilation I have shown here two frame of references. One is S, this is S frame, and this is S prime frame. S prime frame is a moving frame that is moving with the relative speed v, and O is observer in S frame. O prime is an second observer that is in S prime frame, right? So this S prime frame is moving along the positive x direction. This is positive x direction in which this S prime frame is moving. A clock is fixed at this particular point in S prime frame. So a clock in a moving frame will be seen to be running slow or dilated according to the Lorentz transformation. So this is one of the important point, that moving clock ticks more slowly than a clock at rest. So the second point, this point is very important in time dilation, and this statement is according to the observer O. O is in stationary frame with respect to the S prime. He says that moving clock ticks more slowly than a clock at rest. Tick means the needle of this clock, the tick 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 tick. The time interval between two ticks is slower for this observer O in this stationary frame, right? This is known as proper time into the S prime frame for the observer O prime. So the time will always be shortest as measured in its rest frame. So this is the third point in time dilation case, that time will always be shortest in its rest frame. The time measured in the frame in which the clock is at rest is called the proper time. So let us see in detail about this time dilation. So this was the basic thing, that the time according to the Lorentz transformation, the time basically observed by the O observer in rest frame will be dilated. It will be longer, right? So now the time dilation and its description. So we have seen earlier that S and S prime are two frame of reference. S prime frame is moving along positive x direction with the relative speed OV. This is positive x direction. Right. A clock is fixed in this frame, that is a moving frame. O prime is an observer into the S prime frame, and here O is observer. This is x prime, y prime, z prime, and t prime are the coordinate in S prime frame. Here it according to the O observer, the coordinates of the any event will be x, y, z and t. So let a clock be fixed at the point x prime. So here at x prime I have fixed a clock in the moving frame S prime. An observer in S prime finds that the clock produces two ticks at time t1 prime and t2 prime. Right. So t1 prime and at t2 prime the two ticks of the clock noted by the observer O prime. The time interval between these two ticks as measured in the frame S prime is given by T naught, and T naught is the proper time which is measured by the O prime. So the time interval between those two ticks will be T2 prime minus T1 prime. So that time interval is denoted by T naught in S prime frame by the O prime observer. So T naught is proper time, and this time is observed in the moving frame. So remember this point that T naught is the proper time in this particular derivation, and that was noted down by the O prime observer in a moving frame. So what will be the time interval for these two ticks into the moving frame in case of the observer O, that is in rest as with respect to the S prime? So then in rest frame the T is equal to T2 minus T1. The observer basically two ticks, one is the T1 prime and second ticks he listen at T2 prime. This is the time interval between two ticks according to the observer O, and for this observer O the time interval of the same two ticks will be T1 and T2. So here you can see that T is the time interval measured by the observer O. So T is equal to T2 minus T1, and here for the O prime observer T naught is equal to T2 prime minus T1 prime. So this observer, O prime observer, knows the time interval between the two ticks, that is T naught, and that time is proper. So what will be the time interval of those two ticks for the observer O? Right. So by Lorentz transformation we know that T is equal to T prime plus x prime V upon C square upon square root 1 minus V square upon C square. This is in inverse Lorentz transformation, right? So T is the time for observer O. So that formula from the Lorentz transformation you can write here, Lorentz transformation. But the formula which I have written here, that comes into the inverse Lorentz transformation. T is equal to T prime plus x prime V upon C square upon this factor square root 1 minus V square upon C square. And further the time measurement made in the moving frame are made at the same location, right? So T is equal to T2 minus T1 and I am putting the value of this T2 and T1 because T is equal to this one I defined here. So I can write T2 is equal to T2 prime plus x2 prime v upon c square upon square root 1 minus v square upon c square, and similarly for T1. So T1 is equal to T1 prime plus x1 prime v upon c square upon this square root 1 minus v square upon c square, right? And because when I will put the value of T2 and T1, this is T2 prime plus x2 prime v upon c square minus T1 prime minus x1 prime v upon c square. So here we have already mentioned that this clock is kept at x prime point. That means x2 prime is equal to x1 prime, so that is same x prime. So when I simplify it, so this becomes x prime v cancel out, and you get only this result: t is equal to T2 prime minus T1 prime upon square root 1 minus v square upon c square. And further, when you put the value of this time interval which we defined here earlier, that is t naught, so t is equal to t naught upon square root 1 minus v square upon c square. Here I am repeating again that in our assumption we have already made clear that the clock is fixed at the x prime point. So this x prime basically, in case of solving this equation, so x2 prime and x1 prime are equal, and that is x prime basically. So it cancel out because of that reason. So we found basically the time dilation result: t is equal to t naught upon square root 1 minus v square upon c square. This t is the time, basically time interval between the two ticks which appear to this observer O, who is in rest frame, right? And t naught is the time interval for the O prime observer, and that is the proper time. So this is the relationship with this factor square root 1 minus v square upon c square between apparent time and proper time. Further, if we made some observation on the basis of this formula of time dilation, that t is equal to t naught upon square root 1 minus v square upon c square. I am taking one more example here of the muon. The mean lifetime of a muon in its own reference frame, called the proper lifetime, is 2.2 microsecond. So in the next video lecture I will discuss about the muon experiment. So right now I am just taking an example of that particular experiment, because we know that muon are elementary particle, and here I have just taken the lifetime of the muon decay, that is 2.2 microsecond in a frame moving at velocity v. With respect to the proper frame, the lifetime t is calculated by using the same formula with different velocities. So the formula is this one, which we have derived earlier, and case is selected for the muon. The lifetime, proper lifetime of the muon is 2.2 microsecond, that is t naught. I have to calculate t by using different velocity, right? So serial number, I have selected here 6 cases, and in these 6 cases I have varied the speed, right? Velocity, relative velocity 0.4, 0.6, 0.8, 0.9, and then after 0.998 c, and then after c, v is equal to c. And we will see that what happens if we vary the relative speed in case of time dilation formula. So time dilation t in terms of t naught, the value is 1.0910 into t naught. So I am getting t is equal to this value in this case when speed is 0.4 c. and speed is 0.6 c, the value of t is 1.25 multiplied by t naught. By this factor it is increasing, and when speed further increasing, relative speed now 0.8 c, the time dilation further increasing, that is 1.66 of t naught, and when speed is 0.9 c, it becomes 2.294 of t naught, and when speed further near about to c 0.998 c, then you can see speed time basically is 15.819 of t naught. If I simplify it by putting the value of t naught, you can see here that this is 2.2 microsecond, that is 2.2 into 10 raised power minus 6 second. It becomes 2.4 into 10 raised power minus 6, 2.75, 3.6 into 10 raised power 6, 5, 10 raised power 34. And when v is equal to c, you can see here that time t becomes infinite, right? So infinite, so time interval t, basically what was the t? T was the time interval between the two ticks of the clock in rest frame. So the time interval is infinite. The observer O will listen at infinite time interval of those two ticks, and here 34 microsecond, here 5, 3 microsecond, 2.7, 2.4. So as relative speed is increasing, you have seen here that time interval between the two ticks is increasing. It means the proper time of the between the two ticks of the clock, you can say here that was suppose 2.2, but right now that is increasing and increase at infinite time. So the point is shown here with this graph, that on this x-axis I have considered the v, that is the relative velocity as a function of the speed of light, and on the y-axis that t upon t naught is taken. So how basically this varies? So at when v is equal to 0.3 c, 0.4, 0.5, 0.6, 0.7, so ratio between t and t naught is increasing. So when v is equal to 1 c, 1 into c, this v is in terms of the speed of light. So 0.4 c, 0.5 c, 0.6 c, 0.8 c, 0.9 c and c. When v is equal to c, you can see here that it increases sharply. So this behavior basically is for the time dilation in special theory of relativity. So the rest frame, the person who is in rest frame, for that basically the ticks appears slow as compared to the observer O prime that is in a moving frame. So the if the clock, I am repeating again this explanation, that if a person is in a moving frame, right, O prime is in a moving frame, and he observed two ticks, at first tick at t1 prime, second ticks at t2 prime. So time interval between these two ticks will be equal to t2 prime minus t1 prime, and this time interval will be proper time, right, and that proper time is denoted by t naught. And now in case of observer O, who is in rest with respect to this S prime frame, which is moving with the speed v relative to S prime. So this man, this observer will listen these two ticks at two different interval, first at t1 and second at t2. So time interval of these two ticks will be t2 minus t1, and the time interval is defined for that observer is t. So now we have seen that this is slower for the observer O, as we have mentioned in our first slide that a moving clock ticks more slowly than a clock at rest. So where is moving clock? Moving clock is here in the moving frame, right? And rest frame is this one. So you can say that this moving clock time measured by the O prime observer will be proper. I suppose I am considering here that this clock right now 3 o'clock in this here in the moving frame. So this clock is into the moving frame, that is S prime, right? How much time basically it appeared to the observer O, that you can say 6 hours. So for that the time will be 6 hours. So time in difference between these two observation is of 3 hours. So this is the point. So that clock basically is slower for the observer O. So this is the meaning of this statement. A moving clock ticks more slowly than a clock at rest. So he says that that is running slower by 3 hours, right? So I am repeating further again. So right now this clock is in a moving frame and time is exactly 3. So how much time it will appear to the observer O? So I have just taken a simplest example, and in case of the observer O it will appear at 6 o'clock. This is a classical example without any calculation, but to make more clear about this statement. So moving clock ticks more slowly than a clock at rest, or as I have mentioned here in the earlier statement, that dilated time and the running slow. This clock basically runs slow according to which observer? O or O prime? O. According to the observer O, this clock run slow, and for the O prime this run with proper time. So this is the difference between the observation in case of time, right? So one can show all these things with the help of time dilation. So here we have shown the derivation and its concept, and then after the conclusion on the basis of that formula by using the muon example, where we know the lifetime. So how much lifetime it appears in the rest frame, that is mentioned here. So T is mentioned here, right? And that ratio of T with the T naught, as in case of when velocity is 0.1 c, 0.2 c, 0.3. So when relative speed is increasing, so you can see here that T and T naught ratio is increasing sharply, right? Now further, now we will clear more explicitly the concept of time dilation by solving these numerical problems. So here first problem is that what is the mean lifetime of pi plus meson moving with the speed of 0.73 c when the proper life is 2.5 into 10 to the power minus 8 seconds. So in this numerical problem, first of all we have to see that what is given. So given is what? One thing for the pi plus meson, that is speed 0. Given v is equal to 0.73 c, where c is speed of light. This is speed of light, that is 3 into 10 raised to the power 8 meter per second, right? And the second thing which is given here, that is proper life 2.5 into 10 raised to the power minus 8 seconds. Second, the point which is given is T naught. T naught is equal to 2.5 into 10 raised to the power minus 8 seconds. So here you can see that only these two values are given, and with the help of this we have to find out the value of t. So directly here there is no problem in this question to solve that. I have to find out only t. So t is equal to t naught upon square root 1 minus v square upon c square, because in this question they have already mentioned that what is the proper life. Proper life is denoted by t naught, and this is velocity. So given velocity and t naught, now by using this formula, for time dilation, that it is equal to t naught. So I am putting the value of t naught, that is 2.5 into 10 raised power minus 8 second, and this is square root 1 minus v is equal to so you here in this vector I have written v square upon c square, that is v upon c whole square. So instead of v square upon c square I can write v upon c whole square. So v is equal to 0.73 c upon this c and square of it. So now c cancel out, so I am taking a square of 0.73, and by solving that I found this value is 0.73 whole square, and this is approximately 0.5329, right? So I am putting this value here, that is square root 1 minus 0.5329, and further that becomes 0.4671 square root of it, and the result is 0.6834. So square root of this vector is equal to 0.68, and I have in 2.5 into 10 raised power minus 8. So by simplifying it, 2.5 into 10 raised power minus 8 second divided by this 0.6834, I will get this result, that is 3.658 into 10 raised power minus 8 second. That is approximately 3 point insignificant number 3.7 into 10 raised power minus 8 second, and this t is larger as compared to the proper time. Proper time is 2.5. So you can see here in this numerical problem that the observer, basically the scientist who is sitting in the lab, observe lifetime longer as compared to the real time, that is the proper time for this meson particle. And now this second example you can see here. So here in this particular example I have shown that what is the velocity of pi meson whose proper mean life is 2.5 into 10 raised power minus 8 second, and observed mean lifetime is 2.5 into 10 raised power minus second, right? They mention observed, that means a scientist who is sitting in the lab, experimental lab, observatory, measure the lifetime of this pi meson 2.5 into 10 raised power minus 7 second, and that is larger as compared to the proper time. So in this numerical problem also there is no confusion between the t and t naught. So here I can write that t naught is equal to 2.5 into 10 raised power minus 8 second, and t is what, 2.5 into 10 raised power minus 7 second. What I have to find out? I have to find out v, relative speed I have to find. So this is given, all these things are given. So now again by using the formula, which one? Of time dilation, that is t is equal to t naught upon square root 1 minus v square upon c square. So t and t naught is given, I have to find out v. So just rearranging the term, so t upon, or you can write it by taking it in this side. So square root 1 minus v square upon c square is equal to t naught upon t, and now square both the side, so it becomes 1 minus v square upon c square is equal to t naught upon t whole square. And further we have to find out the value of v, so v upon c square is equal to 1 minus square of this term, so v square upon c square is equal to 1 minus this t naught upon t whole square, and further v is equal to this c, and then after square root of it, I am writing directly here now, c is square root of 1 minus this t naught upon t whole square, right? So I have to put the value of t naught and t and c, where c is the speed of light, and the value of that is 3 into 10 raised power 8 meter per second. And here when I will put the value of t naught in second, and again of the value of t in second cancel out, so there is no unit with this factor. Unit will come with this factor, that is c, 3 into 8 meter per second. So I have to find out obviously v, so that will be in terms of meter per second. Now I am putting the value of this, v is equal to c is square root of 1 minus, this is 2.5 into 10 raised power minus 8 upon 2.5 into 10 raised power minus 7, right? And further square of it, this is 10 raised power minus 8, this is 10 raised power minus 7, so if I multiply, this becomes 25 into 10 raised power minus 8, then this factor cancel out, so this is 2.5 and this is 25, so the result of it is c is square root of 1 minus 0.01 after simplification of it and square of that, so it becomes 0.995 c, right? So this is the answer of this particular question. So v is equal to 0.995 c. So now for this particular case where t and t naught was given, so one can find out the relative speed, and that is approximately 0.995 c, near about to this c, but not remember, when you solve this kind of problem and your relative speed comes greater than this c, it means something is wrong in the numerical problem. So it is a checkpoint also. When the answer comes greater than c, for an example 1.5 c, 1.2 c or 2 c, 3 c, because you know that nothing can travel faster than the speed of light, so that will remain either equal to or below that. So here v is equal to 0.995 c, so you can assume that the answer is right. So in these problems you have to put the value of c, that is 3 into 10 raised power 8 meter second, at the last of the numerical problems. Don't try to put the value of c in between the calculation. And one more example I can take here, that is the about a wristwatch. In this numerical problem, what is the statement? A wristwatch keeping correct time on earth is worn by the pilot of a spaceship, right? So the wristwatch basically fixed on the earth and worn by the pilot in a spacecraft. How much will it appear to lose per day with respect to an observer on earth? In this question what they are asking that it will run slow according to the observer who is on the surface of earth, that is in rest frame, as compared to the moving frame. So what is moving frame here? Moving frame is a spacecraft, a spaceship in which pilot is sitting, and wristwatch is basically corrected with the person who was on the surface of the earth, right? So now they are asking that now because of the relative motion between the spacecraft and earth, this clock basically will run slow according to the stationary observer, right? So how much basically that will slow? This is the question. Now the next point, when a spaceship leaves the earth with a constant velocity of 10 raised power 7 meter per second. So in this question the formula is same, that we have to use time dilation formula, and from the statement you can take the flavor of the time dilation formula. And as I have mentioned earlier in the derivation, that there are two things, one is a moving frame and second is the rest frame. So in this numerical problem, what is moving frame? Moving frame is a spaceship, right? And who is sitting there? A pilot. So this pilot will be O prime observer, and this spaceship is S prime frame. S prime frame is moving how much relative velocity with the S, right? So that is 10 raised power 7 meter per second. So all these things basically we have discussed in our first slide, that is this one. There are two frame of references, one is S prime and second is S. S prime is a moving frame and moving right now in this case, that is along the positive x direction with this speed v relative to S. So S is a stationary frame, S prime is a moving frame, clock is in S prime frame, O and O prime are observer in S and S prime frame. So in this particular numerical problem here, a wristwatch is keeping correct time on earth is worn by the pilot of a spaceship. So there are two clocks basically, one is on the earth and second is in the spaceship. So we have to find out the time difference between them, right, according to this relative motion. So how much will it appear to lose per day with respect to an observer on earth when a spaceship leaves the earth with a constant velocity? So clock is in moving frame. The time of this clock is to tell by this observer, right? So it means we have to find out the time, this t, according to the observer O or O prime. So this is the situation. So now first of all, if my statement is clear about this numerical problem, that clock is in a moving frame and the time for that is 24 hours, means 24 hours. How much basically it differ for the rest observer with respect to rest observer, that we have to discuss in this particular example. So first of all, that what is given. So given is 1 day, that means 24 hours, and second thing, this v is equal to 10 raised power 7 meter per second. what formula we have to use? This T is equal to T naught upon square root 1 minus V square upon C square. So we know that if this statement is clear that what is T and what is T naught in this numerical problem, so there is no any single thing to solve the particular question. So now we have to make clear that what is T and what is T naught. This 1 day per day is T or T naught. This is the point, right? So again I'm reading this statement. A wristwatch keeping correct time on earth is worn by the pilot of a spaceship. How much will it appear to lose per day with respect to an observer? So this statement is O prime observer or O. This statement is for O prime observer. So we have to find T naught. And on the earth 1 day is equal to 24 hours. So this is the point only. The T naught we have to find out here, right? And T is 24 hours. The person who is on earth, for that 24 hours means 24 hours. 1 day is equal to 24 hours. So the point is related to the only moving frame. So how much will it appear to lose per day with respect to an observer on earth, right? So we have to find out here T naught. So now you can put the values here. So T is equal to 24 hours is equal to T naught upon square root 1 minus V square upon C square, where V, you know, that is given, and this value also V. I forget to put the value of V here, so I am using second page that T is 24 hours. T naught we have to find out is square root 1 minus V is equal to 10 raised power 7 meter per second, and this is C, that is also in meter per second. 3 into 10 raised power 8, I am writing by this way, and is square of 8. So you can find out this is T naught is square root 1 minus, this is 10 raised power 7 or this is 10 raised power 8. So 10 power 7 cancel out by this, and here is only 10 into 3, that is 30. So 1 upon 30 whole square. I am simplifying it, and that is basically you put here 1 upon 30 is equal to 0.033 like this, and then square of it 1 upon 30 square, that is 0.00111, and then after 1 minus 1 upon 30 whole square, that is equal to 0.998889, and then after square of it 1 minus 1 upon 30 whole square, and that is 0.9944. So now putting the value, so it becomes T naught upon 0.99944, and there is 24. So you can write it by T naught is equal to 24 into 0.99944, and the result of it is here, that is T naught is equal to 23.9866 hours. Right, so this is T naught. So you can also compare the result that T is 24 hours, so T is the time. If you want to verify that you have selected T and T naught perfectly or not, so you can see here T naught is 23.98 and it appears 24 hours. So 24 hours is larger as compared to the 23.98. So the statement according to the time dilation that moving clocks tick slowly, right? So this clock run slowly, which you have seen here in this statement, that a moving clock ticks more slowly than a clock at rest. So this statement is verified here. So T naught is smaller. T naught is the proper time, and T is the time basically which observed by the observer O. So now the time difference between these two hence loss you can find out, loss in one day, that will be equal to 24 hours minus 23.9866, and that is 0.0134, and this is in terms of hours, right? So further you have to convert it into minute and then after into second. So 0 in terms of minute, this is 0.804 minute. In terms of second, multiply it again with 60, so this becomes 48.24 seconds. So this is the difference. So according to the observer O, the clock basically will show this difference as asked into the question, that how much will it appear to lose per day with respect to an observer on Earth. So this pilot basically find the result that according to the observer O, that this much time I am losing. So how much time he lose per day, that is 48.24 seconds, right? So this statement was of the pilot, and now pilot can assume that per day he is losing 48 point something seconds, right? So this is the observation of pilot in a moving frame. So by this way one can understand the numerical problems related to the time dilation, and this is an interesting topic. So one more example I can take here in case of time dilation, that is basically related to this particular question: how fast must a spacecraft travel relative to Earth for each day on the spacecraft to correspond to 2 days on Earth? So in this numerical problem, how fast must a spacecraft travel? In this statement the question is clear that we have to find out the velocity relative to the Earth for each day on the spacecraft. Each day on the spacecraft. Spacecraft is a moving frame, and the time on the moving frame is denoted by T naught. So one day will be T naught, correspond to 2 days on the Earth. Here Earth is a rest frame and time is given 2 days. So from this numerical problem it is very clear that we have to find out V. Given is T naught, that is 1 day, that means 24 hours, and T is given the time on the earth, that is 2 days, that means 2 into 24, that is equal to 48 hours, right? So now you can find out the velocity by using the formula T is equal to T naught upon square root 1 minus V square upon C square. So here T is also given, that is 48, T naught is 24, and this is 1 minus V upon C whole square, right? So again rearranging the term, because we have to find out V. So by rearranging the terms, this, as we have solved earlier the numerical problem, is square root 1 minus V upon C whole square is equal to 24 upon 48, and 24 by this 22 times, so 1 by 2. So when you will take the square of that, right? So now squaring both the side, so it becomes 1 minus V upon C whole square is equal to 1 by 2 whole square, 24 1 ja 1 and 2 to 48. So 1 by 2 is square of 1 by 2 is equal to 1 by 4. So this is 1 by 4. So now further I have to find out V. So rearranging the term, V upon C whole square is equal to 1 minus 1 by 4, that is 3 by 4. So you can say that V is equal to square root 3 by 2C, and square root 3 you know, that is 1.732. So when you will put the value in and simplify and further the value of C, then it becomes 2.598 into 10 raised power 8 meter per second, or in approximately V is equal to 2.6 into 10 raised power 8 meter per second. So these were some basic example related to the time dilation, right? And I have discussed here some points related to the stationary frame and a moving frame. So that phenomena you can see here with this simplest example, that the person is standing on the earth and this is a spacecraft, right? Or I can make it in a proper way by standing this person in this side and coming towards that. So this is a moving frame, this spacecraft is a moving frame, the person is standing on the surface of Earth, the moving clock is this one, right? This is moving clock, this clock is in spacecraft, and here an observer, that pilot that noted this time, that will be T naught, and the time measured by this person who is standing on the surface of Earth is this one, right? Though this time difference, there are two frame of references, one is related to the Earth, second is related to the spacecraft. The pilot of this spacecraft is O prime, and here this person is an observer O, right? And it's a clock, this one, and time. So what basically is relationship between the time, right? Because of the relative motion of this spacecraft with respect to this person. So that basically explained with the help of the time dilation, and I have selected here some basic example to make this idea more clear. But if you have any problem related to any numerical or conceptual problem, you can ask and write that message below this video. Thanks for watching this particular video.